So welcome back to the Advanced Linear Algebra. So what we have been doing so far, we talked about the very fundamentals of matrices, actually understanding the matrices in its canonical form. So we started our discussions in our previous two lectures. We started our discussion with square matrices, and we kind of proved that square matrices have eigenvalues, must have eigenvalues, and then we also showed that at most a square matrix of order n can at most have n eigenvalues. And then we talked about characteristic polynomials, minimal polynomials, the relationship between minimal and characteristic polynomials. Then we talked about the different kind of multiplicities, algebraic multiplicities. We talked about geometric multiplicity, minimal multiplicity, and then we also talked about so-called the Cayley-Hamilton theorem, actually. So we discussed the several things about the matrices and the theorems related with the eigenvalues and eigenvectors. So now we would like to move towards what we call another important topic of the diagonalization, actually. In one of the previous lecture, I already have talked about that diagonalization, kind of why the diagonalization is interesting and important, actually. Because if you are able to diagonalize a matrix, then you can compute the higher powers of this matrix very easily, actually, and very efficiently. Okay, so you don't have to do a lot of messy calculations, or even your computer or algorithm do not need to do the messy calculations to compute the higher powers of the matrices, and that's what makes it important. Okay, in applications part later, I will talk about, for example, one particular example, which is going to be about the Google PageRank algorithm. So the Google PageRank algorithm is an algorithm. It's a kind of a probabilistic algorithm, actually, developed by some of the people at the Google, and it was used some years back by Google to rank the website. So in other words, when you make a search, actually, Google's try to find the relevant websites to your search and tries to rank them, actually, that okay, which one is more important. For example, if you search Sukkur University, you will see, interestingly, that the official website of the Sukkur University appears first, actually. And then as you go down, actually, you're going to see that more and more less relevant websites are appearing, actually. Okay, so how Google knows that this website is important, so let's keep it at top, and these websites are not important, so let's keep them down, actually. So based on this algorithm, basically Google kind of ranks the websites. And in that algorithm, okay, one important dimension of the algorithm is basically played by computing the higher power of a matrix consisting of some kind of probabilities, actually. Okay, so we will talk about it later. So my point is this, that computing the higher power of matrices is an important phenomenon, actually. Okay, and computing the higher power of matrices becomes very important, very easy if your matrix is diagonalizable. Okay, so that's what we are heading. So let's start with our discussion on diagonalization. So we will start our discussion first by talking about some of the fundamental results and maybe notions about the similar matrices. I hope that you already know that when two matrices are similar to each other, but I would like to give a quick review of those, because then I will use them later in my results to study the diagonalization, actually. Okay, so let's just start with what you call the similar matrices. I mean, if you know it already, you can ignore this part. But if not, there is no harm in reviewing some of the basic results. So what are similar matrices? So if you take, for example, two square matrices of order n with entries from the field F, where F can be field of complex numbers or the field of real numbers, then we will say that A is the matrix A is similar, okay, to B, and I'm going to denote this by, mathematically denote this by, I'm going to say that A is similar to B, so this tilde is going to be the symbol to show the similarity of A with B. If we can find an invertible matrix, okay, we can find an invertible matrix P, okay, from Mn, such that A can be factorized in the terms of B in this manner. In other words, such that A can be written as P inverse BP, or the PA equal to BP. So if one of these identity holds, you're going to say that A is the matrix that is similar to the B. And this matrix P, so we're going to call this matrix P similarity matrix. Okay? We're going to call this matrix P a similarity matrix. Okay. So what is the next thing? The next thing, maybe a quick remark, is that we can easily prove that this similarity relation is an equivalence relation actually. Okay? It's an equivalence relation. That is, you can show that every matrix, every square matrix is similar to itself, okay, by taking the similarity matrix as identity. Because if you take, say, identity inverse and multiply with A identity, you're going to get, again, matrix A. So A is similar to itself. So the next is that this similarity relation is symmetric actually. In other words, that if A is symmetric to B, then this implies that B is symmetric to A actually. And it's not difficult to see that if A is symmetric to B, then there is a similarity matrix P such that A can be written as B inverse BP. Now, if B is similar to A, let's take similarity matrix S to B, for example, P inverse actually, and multiply the S inverse with A actually from left and right. And if this will be the case, you can see by substituting the value of A, so SA is P inverse BP and S inverse, okay, S inverse, and S is P inverse, so so I need to put an inverse here and S here actually, okay. So this is not going to be inverse. So S inverse is really P inverse B, P and P actually, and it ultimately gives you B. So what does this shows? That B is similar to matrix A because there is a similarity matrix S actually. Similarly, you can also see that this relation is reflexive, that if A is similar to B and B is similar to A, you can say that A is similar to C actually. So this similarity relation is really an equivalence relation actually. So what I'm going to do now, I'm going to put some of the basic properties of the similar matrices that I'm going to use later on in my discussion on diagonalization actually. So you can treat this as a theorem or proposition, whatever you call it. So it goes like this. So imagine, let's take, you take two matrices, square matrices, such that A is similar to B. Then what can be shown? That these similar matrices are not only similar, but they share the determinant actually. Okay, their determinant is equal. Not only determinant, but their traces are also same actually. And third is that if in addition to A being similar to B, if we assume in addition that A has full rank, in other words the rank of A is equal to n, which is the dimension of the space Fn. So in other words, it has a full rank. Then the rank of A is also equal to the rank of B. So in other words, if A has a full rank, then the rank of the similar matrices are also equal. Fourth property is that if A and B are similar, what you can show is that A minus xi is also similar to B minus xi for all, maybe I must write lambda, for all lambda in F actually. Okay? And moreover, you can also see that for some lambda, if A minus lambda I is similar to B minus lambda I, okay, then A is also similar to B. In other words, converse is not true in general, but if for those lambdas for which this is true, A minus lambda I is similar to B minus lambda I, then A is also similar to B. So these are some of the basic properties that we're gonna use again and again at several places actually. I'm gonna prove some, maybe one or two, and leave the two for you to do as an exercise. Okay. So for example, let me quickly prove, say, part 1 that why this is true. Now, since A is similar to B, so the A can be written as B inverse BP. So the determinant of A is going to be the determinant of this product, B inverse BP. And hence, you can say that this is same as the determinant of the product is the product of determinants of B times determinant of P actually. Okay, you can again put these two determinants together and you can say that this is same as determinant of P inverse P times determinant of B. Okay, the determinant are numbers, so you can multiply this number with this, which is same as calculating the determinant of P inverse P, and hence this is going to be the determinant of identity matrix multiplied by the determinant of P, and the determinant of identity matrix is 1, so this is equal to determinant of B. So this shows really that the determinant of two similar matrices is equal actually. You can also show that that it's not difficult to show that the traces of the two matrices are same actually. So let me show, say for example, third part, which says that if you have a matrix A that has a full rank, okay, then the rank of A must be equal to B. In other words, then B also has a full rank actually. So if A has a full rank and A is similar to B, then B also has a full rank. So this is what that we would like to show. Now, as it is given that the rank of A is n, okay, then what would be, then what is the rank nullity theorem? So if you apply rank nullity theorem, the rank of A plus the dimension of the null space of A, if you put together, you're going to get n actually. Okay? But since this guy is equal to n, so this means So it's equal to the dimension, we say Fn, which is equal to n. So this is n and this is also n, so this means that the dimension of the null space of A is equal to 0. And if the dimension of null space of A is 0, then this means that null of A is equal to 0. Okay? Null of A. So the null of A is equal to 0 subspace. My claim is that null space of B is also 0. Okay? The null space of B is also 0. Why it is 0? Take, for example, a vector V from the null of B. Okay? Then this is going to show that BV is 0. I can say, for example, multiply P on both sides. I can say that PBV is going to be what you call equal to P0, so which is going to be 0. PBV, you know, by the definition of what do you call the similarity, I can say that this is going to be same as A P inverse V equal to 0. Okay, and this means that P inverse V belongs to the null space of A. But the null space of A consists of only 0 vectors. So this means that this P inverse of V must be 0. And if the P inverse of V is 0, then if you multiply P onto both sides, okay, if you multiply P onto both sides, so it turns out that V is 0. So this shows that you took an element from the null space of B and it turns out to be 0. Now if the null space of B is trivial, okay, it's a trivial space, that means that the dimension of the null space of B is also 0. So what would be the rank of then matrix B? So it is going to be the dimension of Fn. The same is also valid for matrix B, minus the dimension of the null of what do you call B actually. And but the dimension of null of B is 0, so the rank of B is also going to be n. So this shows that if A has a full rank and A is similar to B, then B also has a full rank. So these are some of the basic properties. You know, you can easily show that, you know, maybe this is an exercise for you to show that, you know, if A and B are similar, then A minus lambda I and B minus lambda I, they are also similar. Okay? They are also similar. So what is the next thing that I'm interested in? Now I want to move towards another step towards diagonalization, which is going to be, maybe you can ask the next question, okay? If the two matrices are similar, how about their eigenvalues? Are they similar? How about their characteristic polynomial? Are they similar? How about the geometric and algebraic multiplicities, different kind of multiplicities? Are they also same actually? The answer is yes actually. So if you have two matrices, their characteristic polynomials are same, their what do you call, eigenvalues are same, their geometric and algebraic multiplicity of the eigenvalues are same, so everything is same actually if the two matrices are similar. So this is what I would like to prove next actually. So let's take, you have two matrices of order n, then such that A is similar to B, okay, then the characteristic polynomials of A and the characteristic polynomial are same, This is interesting. And hence, since the polynomials are same, their roots are also going to be same. Eigenvalues are same. Okay. Moreover, all these eigenvalues eigenvalues have same algebraic and geometric multiplicity because they have same algebraic and geometric multiplicities. So this is an interesting result that we're gonna prove. So the proof is really straightforward actually. It's not really difficult. For example, let's start with computing the characteristic polynomial of A. Okay, the characteristic polynomial of A. Now, what is the characteristic polynomial of A? It is the determinant of x minus xi minus A. Now, we just proved that if A is similar to B, then xi minus A would be similar to xi minus B. They are also similar. And if these are similar, their determinants are also equal. So I can say that this determinant is equal to determinant of xi minus B actually. Okay? Because these two matrices are similar. And if they are similar, their determinants are equal. And if this is equal to the determinant of xi minus b, this is what? This is really the characteristic polynomial of the matrix B actually. So this shows that the characteristic polynomial of the matrix A is same as the characteristic polynomial of the matrix B if A and B are similar. You know, and why the eigenvalues are going to be same? Because the eigenvalues are the roots of the characteristic polynomial. Because both polynomials are same, so their roots are also equal actually. Okay? So eigenvalues are same trivially. Okay? Trivially. How about algebraic multiplicities? Okay, how about algebraic multiplicities? The algebraic multiplicity is, what is algebraic multiplicity? So for example, you take an eigenvalue lambda, okay, lambda be eigenvalue of matrix A actually. Okay. Then of A. Then this eigenvalue is going to have some multiplicity. In other words, in the characteristic polynomial of x, okay, in the characteristic polynomial of x, this term x minus lambda will appear say d times. So it's going to be something else. So there is also going to be some other terms actually. Okay, but I'm interested, for example, only in the multiplicity of the term x minus lambda. So in other words, the lambda has multiplicity d in the characteristic polynomial of A. But the characteristic polynomial of A is precisely equal to the characteristic polynomial of B actually. So this means that this lambda also have the same algebraic multiplicity with reference to the matrix B actually. Okay? So the algebraic multiplicities are also same actually. It follows trivially. How about geometric multiplicity? Let's think about the geometric multiplicity, that why the geometric multiplicity is same actually. Okay? Now, if A is similar to B, what is geometric multiplicity? So again, say for example, take an eigenvalue, lambda be an eigenvalue of matrix A actually. Okay, and let's say that G lambda is the geometric multiplicity, okay, with respect to, for example, matrix A. Okay, let's denote it by G lambda, but with respect to the matrix A. Now, what is the G lambda? G lambda is the dimension of the eigenspace of the matrix A, eigenspace of the matrix A associated with lambda actually. This is what is the dimension of it. But this dimension, okay, is equal to the n minus rank of what do you call the operator A minus lambda I. So we proved this identity in our last class as well, that the dimension of the eigenspace plus the rank of this operator is equal to n actually. So this dimension must be n minus rank of A minus lambda I. But the rank of A minus lambda I, due to similarity, is same as the rank of B minus lambda I. Okay? And therefore, we're going to say this is same as, this is equal to the dimension of the eigenspace of the matrix B, you know, as what do you call, for the eigenvalue lambda. But now we are treating the lambda as the eigenvalue of the matrix B actually. And this means that this is equal to the geometric multiplicity of the lambda, but with reference of the matrix B actually. And hence their geometric multiplicities are also, what do you say, equal actually. Okay? So what does this show? If two matrices are similar, they have same eigenvalues, they have, what do you call, same algebraic multiplicities, same geometric multiplicities, and so on and so forth. Now let's move towards the diagonalization and let's prove our first important result. Okay? Let's prove our first important result actually. And this result also has to do with the algebraic multiplicity. So the result says that imagine you have a matrix A, and this is a strange kind of a matrix in which all eigenvalues have algebraic multiplicity equal to the geometric multiplicity. Okay? So algebraic multiplicity is equal to the geometric multiplicity. Then the eigenvectors associated with the eigenvalues are going to create a basis for the vector space Fn actually. Okay? So this is what really the next lemma is. We will do several examples as well, so you have to kind of bear with me. So let A is a square matrix, okay, and it's kind of a square matrix that for each eigenvalue, in other words, the element from the spectrum of the A, for each eigenvalue of A, we have, let's put say if, this is going to be the more better, and for each eigenvalue we have algebraic multiplicity equal to what we call the geometric multiplicity. Okay? Algebraic multiplicity equal to the geometric multiplicity. Then the eigenvectors. So if you put together all the eigenvectors are the spanning eigenvectors for each lambda in a set, that set is going to create the basis of Fn. Then the eigenvectors of A, the eigenvectors of A constitute basis for Fn. Okay, so they constitute the basis for Fn. It could be Rn, it could be Cn. So you have a matrix for which every eigenvalue